Hey everybody, and welcome to another Learning Statistics with Jamovi video. How do I do that in Jamovi? That's the series that we're doing today. And in this one, we're going to continue our t-test tutorials, t-test tutorials, and we're going to do the last one. So in a couple of previous videos, we did one sample t-test, and we did independent samples t-test. Now we're going to do paired samples t-test. So instead of an independent variable with two between groups, independent groups, we're going to get two measurements on the same variable from the same person. Two measurements from the same person on the same variable, set a slightly different way. There we go. And so we're going to open a data set from the folks at Learning Statistics with Jamovi, the textbook. We're going to open up one of their data sets, and we are going to have some fun with that. So before we get started with that, I just wanted to let everyone know, as per usual, we are using the most recent build of Jamovi, version 2.3.3. Now, if you take a look at their release notes on their page, they released a 2.3.6, but I think they only released that to certain regions because there were some errors with some regions in Asia that the program was crashing. So this is the current release for this region. I'm in the United States, so you probably guessed that, but that's where we're at here. And I don't know if I mentioned in the last episode, since this was released in April, in my previous videos, 2.3.3 added a buttload of new languages. Finished up Spanish, Norwegian, French, other Danish, I think was another language. Let me open up. What happened to my German, Italian, Ukrainian, and Russian? So sorry, Danish was not on there, and French. French, German, Italian, Norwegian, Ukrainian, Russian, and thanks to the translation team, that's pretty awesome. That is pretty darn awesome. Okay, so let's talk about within subjects or paired samples t-test. So let's open up one of the data sets. So I'm going to go to the hamburger menu here, and we're going to go to open, and I already got the data library, and so I already have the data library open here to the ls-data. So this is the module that you would add over here in this far corner. You would add the Lsj Data module to your version of Jamovi once you have it downloaded. And it doesn't need to be updated because all it does is just plop a folder in your Jamovi folder, wherever that might be, whether you're using Mac or PC. And so I'm using Mac, and that's why I'm using 2.3.3, but I think PC has 2.3.9 in there somewhere. I don't know. I don't use PC or Windows anymore, so I appreciate all of the people who watch and then are using PCs and sort of ignore what I say about Mac and all that kind of stuff, because once you get into the program, it's functionally the same. There's just a few variations when it interacts with the OS, All right, so we're in the Lsj Data Library, and you can see that they haul their data files. Now, these data files, again, follow the textbook themselves. The flow of this course is not so much the same as that textbook. I'm actually using a SPSS for Research Methods companion guide for Beth Morling's Research Methods in Psychology textbook. This particular guide for SPSS is by Georgiana Wilson Dungas. I still don't know how to pronounce her last name there, but Georgiana Wilson, she's up at the University of Wisconsin, Green Bay. So take a look. You can catch her on Twitter. It's an amazing guide. It really is. And so that's the kind of flow that I'm using, although I am changing the order a little bit on her guide. So we're going to do paired samples T right now. And I'm sure that entire introduction you've probably skipped. All right, so let's talk about which one we are going to do for t-tests. Now, I believe we have done the Zeppo and the Harpo, and we need to finish with a Chico. So student grades in Dr. Chico's class. So these are all joke names referencing the Marx Brothers. So let's go ahead and open up the Chico data set. So this is terms or grades in Dr. Chico's class. And so let's expand these so we can see the whole thing. So this is a paired samples t-test. So Dr. Chico is assessing his students. You probably hear my chair squeaky. It's testing students on a test. Okay, so we have 20 students, as you can see here, and they have 2 test grades. These 2 test grades are going to be our paired samples. And so we are going to use this to talk about paired samples T, all sorts of things referencing effect size, assumption checks, and then the output verbally. I do want to say, for those of you who are watching this video, if you didn't catch my community post, later this summer, I'm going to start making a similar kind of video series to what I'm doing now. But instead of focusing on the output and the process of clicking buttons, we're going to write small result sections. These videos are probably going to be a little bit longer because it's going to show me typing in real time. And I'm pretty self-conscious about that. So there's going to be a lot of errors as we write those. So stay tuned for that. I'll keep referencing that as we get closer and closer until, I have the time to actually do this, of course. But This was a great idea from a commenter, and it's really going to help me in my teaching next year when I've got a full year of research methods and statistics for we changed our major and stuff. So this is going to be a great one. All right. So 2 tests. Let's talk about how to do paired samples t-tests in Jamovi. So how we get started is we have our data set up as we need to, and we're going to go to t-tests, obviously, and we are going to click on that. And we did one sample in independent already. Now we're going to click on paired samples t-tests. So we click on that, and we get the basic paired samples t-test table ready to accept its input. Now, before I do that, I want to actually I'm going to go through the options first before I start putting stuff into the paired values here. So let's start with tests here. So for the tests, student T is the default, but you can also do a Bayesian analysis here by clicking on Bayes factor and putting in a prior value, but you have to know what the prior value is going to be here. And if for perchance you need to use ordinal data as your dependent variable, then you will use the Wilcoxon rank test. So this is a non-parametric test for ordinal DV, for an ordinal DV. Of course, we don't have an ordinal DV. We have 2 continuous variables because they're grades on a test. These are ratio level variables, and they will change on an infinite scale in between 0 and whatever the highest value of this is. Okay, so that's what Wilcoxon rank test is for ordinal level data, or if you violate the assumptions of the paired samples t-test, which are all based on the difference score that is created doing the paired samples t-test. In the hypothesis, we can either do this two-tailed test, which is that our pairs are not equal to each other. We could do one of 2 directional tests, that one of our pairs is greater than the other or in the other direction. So greater than or less than if we're using measure 1 as our sort of reference level. Okay. I always prefer, even if I do have a directional hypothesis, I always prefer doing a non-directional test because it is a more conservative test. That is to say that if we use alpha of 0.05, which most of the time we do for the level of type 1 error that we're willing to commit, this spreads out that 0.05 to both tails, and so it makes it more difficult to detect an effect unless it's very extreme, which I appreciate. So we're going to go ahead and do that. Okay, missing values, exclude cases, analysis by analysis is always the best idea, but you could also exclude cases list-wise. So if they have any missing data for any test, then they're going to get excluded from that. So you always want to do analysis by analysis, in my view. If that option's available, do that. That means the cases are excluded less often unless they cannot contribute to the particular test. Okay. So I do that. For additional statistics, I always like getting my mean difference in there. So it puts that in and it gives you the standard error of the difference. You're welcome to get the confidence interval in there as well. And you can set that confidence level. I always appreciate being able to set the level and not being forced to do 95%, although 95% is a very good confidence interval. I'm not going to click it on this one because it's going to make the table that we are creating here quite a bit messy. So we're going to ignore that. But I am also going to get Cohen's D here. Now, this is the Cohen's D for paired samples, which is a slightly different formula to the independent samples Cohen's D that everyone is perhaps more familiar with. And you can get the confidence interval for that. I do enjoy getting the confidence interval for my effect size because effect size is going to be something that is that is potential to change from sample to sample. But if the effect is a particular size, small, medium, large, or even larger than large, we have an idea of the range of those of that effect size with our confidence interval. So I enjoy getting that. I'm also going to go ahead and grab the descriptive statistics and the descriptive plots. It's always nice to get the descriptive plots. It'll just place the two. Once we get our data in here, it'll just place the 2 next to each other with the mean, confidence interval, and the mode. So it'll give you error bars as confidence interval bars instead. And then the last thing is to get the normality test, the Shapiro-Wilk test, which tells us whether or not our difference score created by subtracting test 1 from test 2 is normally distributed or not. So stay tuned for that one. Let's go ahead and do this here. So couple of ways you can do this. You can grab your first one and click it over. Now you can see here that it wants a pair for this. So you have to give it a pair because you can see grade test 1, null. We've got students T and then dots for everything that's missing. It's looking for its pair. So the other thing you can do is and then it'll go down one line and you just click it over and voila, there it is. You can also, as I pull these both out, you can also click on the first one, hold shift or command in this case, and put them both over and it will make sure to put that into a pair. Okay. All right, so let's look at this output. This is quite a bit of output, so we'll go through. So the first thing I want to do first is talk about the normality test, because if we somehow violated, I'm gonna go ahead and put up the Wilcoxon W there. If we somehow violated normality, we might have to use the Wilcoxon rank test. In this case, we didn't. This p-value is very high, and when you have a very high p-value on an assumption test, you can be rest assured that you did not violate the test at all. You've not violated it. So I would not worry too much about this, but I did want to put up the Wilcoxon W so you could see how these two are different to each other, and most appropriately that they're, because the Wilcoxon W is doing a non-parametric ordinal based test, instead of Cohen's D, it is using the rank by serial correlation, which is a correlation you would use with nominal or ordinal level data, okay? Instead of a Pearson's product moment correlation, okay? So let's talk about Shapiro-Wilks W as opposed to Wilcoxon's W. I think we need a little difference here. In any case, we have a W that's very close to 1, and so that means this p-value is pretty high. And so we did not violate normality, and so we can use students T as much as we want. Before jumping up to the t-test itself, let's look at the descriptives. So we have 20 grades for each test, and the mean for grade test 1 is 57, and the mean for grade test 2 is 58.4. So a difference of 1.4. Look at that, 1.4. Excellent. Then we can see the medians of each. So the median for grade test 1 is actually slightly higher than its mean, if we put them both in my Zoom circle here. And the median for grade test 2 is actually also higher than its mean, which is a good sign here. If we're trying to test the hypothesis, will suggest that the intervention of learning the statistics or learning the material or whatever you did in Dr. Chico's class, learning that improved scores from test 1 to test 2. Okay. And then you can see here that standard deviations and standard errors are fairly equal across the board, which gives us some good insight in being able to do this paired samples t-test. It's very good. Okay, so let's take a look at the t-test itself. So students T comes out to negative 6.48. Now, the reason why it's negative is because this number's mean is smaller than grade test 2. It's smaller, and so when we do, I wish they put a subtraction sign here, but if we put a subtraction sign there, we would get a small number minus a big number, which gives us a statistic of a negative T. Now, you can switch them if you want to. It doesn't really matter. You can put grade test 2 in front of grade test 1, and the only thing that will change is that this negative sign goes away. And that's because T is symmetrical around 0. The T distribution, so all values of T are symmetrical around 0. The mean of T is 0. And that occurs when you subtract the same number from itself, and you get a 0 in the numerator divided by who cares? It's going to be 0, right? So the mean of T is 0, and everything else is symmetrical around it. So a statistic of negative 6.48 is the same thing as positive 6.48, okay? So we have 19 degrees of freedom. That's because a paired samples t-test is n minus 1, where n is the number of difference scores. But because we have equal numbers of difference scores, generally speaking, we just do n minus 1. 20 minus 1 is 19. And so if we were to look that up in a table, we would be assured that our p-value is less than 0.05, because that's how we would look it up in a table. But because we're using a computer program that can find the exact p-value, we get that. But of course, it's very small. A statistic of 6.4 anything, 6 point anything is going to be more than 3 standard deviations. And so we're talking about extreme values in those two tails. And here we're specifically speaking about the negative tail. So our p-value is very small. I wouldn't be surprised if this is like 10 to the negative 5 or 10 to the negative 6, to be honest with you. Somewhere around there. Mean difference, as we already calculated, was negative 1.4. If you were to put grade test 2 first, it would be positive 1.4. Standard error of that mean difference is 0.217 for both of these, because the mean difference for the Wilcoxon W and students T do not change. Now, Cohen's D is a gigantic effect size. Again, Cohen's D is also symmetrical around 0. So negative 1.45 is the same thing as positive 1.45. So you could just take the absolute value of this if you'd like. So negative 1.45. Now, Cohen's D, generally for both independent samples and paired samples, is around 0.2, 0.5, 0.8. 0.2 is small, 0.5 is medium, 0.8 is large. Well, we are fantastically over that. And that's because the amount of variance around these two means is very tight, which means that even a difference of 1.4 units on these tests is very dramatic. It's dramatic, the amount of difference, the amount of improvement these students made in this canned example. And you can see here that our confidence interval does not include 0, which is incredibly important. And the upper limit, or I should say the lower limit, if you were to take the absolute value, the upper limit is still a large effect size, because that's 0.81. That's still large. And so even the lower effects, even the lower bound, or potentially if you want the absolute value, the upper bound of 2, that's a significant effect size. If I were to draw these two distributions, they would be very tight distributions. you're not seeing. I'm not even going to try to draw. There'd be very pointy distributions that were very far apart. That's how you would view these things. And here's the plot again: means, and with 95% confidence interval around the two means, and then the two medians are squares. Now, I would prefer these plots to have standard errors, but you can't change that. So, oh well, just plot them yourself. I would also use either a line graph or a bar graph to show the change. Maybe a line graph would be nice because it would show a nice boop, but you'd have to give a full scale on this one. The idea with the standard error bars is that they're going to be very tight around that mean, and they're not going to overlap, which is going to show you that the effect is very big and significant. So that's how you do a paired samples t-test in Jamovi. If you have any comments, suggestions, or feedback, please leave those down below. Thank you for watching this video. See you next time.